So I'm Dmitry Levin, and today I'll be talking about set version package dependencies. This is a thing we implemented in our repositories and distributions in 2010 to address the problem of shared library updates. So what's the problem? Every time a shared library is updated, there is a risk that, or when not just when a shared library is updated, when a client of a shared library is updated, or even if a new client of a shared library is installed, there is a risk of incompatibility between the shared library and some of its clients. This happens in repositories when the shared library is updated. It's much rare case when an application in repository is updated. It's usually it's compatible with shared libraries it used during the build, but sometimes it can happen. But mostly it's a shared update. But in installations, you can get these incompatibilities both when you're updating from a not very good package repository, when you're doing a kind of selected shared library update, when you're just updating the library and not everything that's built with it, or when you're doing a selective update of a client, or just installing a client from somewhere, not necessarily from the same repository. So this is a kind of unavoidable risk that an incompatibility could happen. So we usually want to control this, and at repository level we would like to stop this, and also in installations. So what kind of ABI incompatibilities are problematic? Spoiler alert, any incompatibilities are really problematic, but some are more problematic, or maybe you can encounter them more often. I separated them in three groups. By the way, you can detect them. So first, the biggest one is those that can be detected on the ELF level. So when ELF symbols are removed or added, or when the name changes, that kind of incompatibilities. By the way, not just removal of symbols is problematic, but also an addition, because well, when you are adding a new symbol to already existing versioning, or just an versioning symbol, this breaks forward compatibility, which is important when you are installing third-party clients, for example. So they could be built with a newer library that you have. So yeah, and when you're changing, you shouldn't really change version of a symbol, but some projects are not aware about this, and they do, and changing of version is even worse than, almost as bad as removing symbol. Well, some other kinds of incompatibilities that you can check at dwarf level, like changes of function signatures in an incompatible way, or types of variables, or, well, what is incompatible way? For example, like a number of arguments of function changes, or the size of the variable changes. It's not as easy as it sounds to define formally what is incompatible change. I'll talk about it a bit later. And all other kinds of ABI incompatibilities that don't reflect on the ELF or dwarf level, just when semantics changes. For example, someday used to be a meme-CPI implementation in GNU-libc that was working on traditional architectures like move, and then it was changed because it wasn't fast enough, and it wasn't formally a part of ABI contract. It was not documented to work as move, but anyway it was changed, and it was an incompatible change from application point of view, that a lot of application were relying on this undefined behavior, that kind of thing. So why all these problems arise? It's because shared libraries are too easy to produce. You just add an option to GCC, and if you're using AutoTools, it's as simple as changing libraries to LT libraries and A sources to LA sources. It's too easy to make them. But to maintain ABI stability is really hard. It requires intelligent design and quite technical skills, and the entity threshold is really high. So yeah, the classic paper on this is how to write shared libraries, and its part describes maintaining APIs and ABIs. It's 8 pages of technical text, so I would say it's pretty high. So that's why a lot of projects are not aware about this, so they do whatever they think is appropriate. In most cases, it's wrong. And even experienced people can miss the problem. This is a example from, I have a lot of examples of ABI breaks, so I'll just show you one from 2016, when due to there was a minor version update of OpenSSL library. It was expected to be just a security fix of one of these security fixes that have names nowadays. So it was just a minor update that removed some SSL2 code from defaults, but also it removed like some functions from libSSL. And it was clearly missed by maintainer because he didn't expect that kind of thing in a minor update. But in case of OpenSSL, he probably should have expected anything. But anyway, it was too easy to miss without proper tooling. So we were very close to repeat the same mistake in our repository, but while I am showing you this example, because the set versions just got this removal symbols. So next day, these missing interfaces were resurrected, but quite a few people were just caught in errors. Because no diagnostics, just application doesn't start anymore. So what could be done about it? The first level of defense is, of course, a classroom. We should educate our students how to write shared libraries properly. But, well, it's not going to happen with all students, I'm afraid. So the second level of defense is our repositories. We should have tooling to detect all these ABI incompatibilities as early as possible. And, well, it's not really that easy. I mean, it's hardly possible to do it without human intervention, because we will have a lot of tools that compare ABIs of libraries, but they have false negatives, so they report there is an incompatibility, but at the same time, human eye can spend a few hours and tell that they are actually compatible. So it's easier to say than to implement, but at least some simple things that we can do. We can at least ensure that applications that use interfaces from libraries are actually linked with these libraries, and we can have tooling in repositories to check that no application, at least in the repository, is linked with 2 different versions of the same library. When the surname of the library changes and not all its clients are built, there is a chance that in some client 2 versions of the same library will be loaded with very bad consequences due to very powerful F symbol resolution algorithm. So the repository defense line is not enough, and we have to implement probably the last line of defense in every installation. When the dependency solver works, it should at least ensure that every library that is required is provided by something, and every library interface is provided. I think nowadays, like all repositories implement this, both dependencies on libraries and on library interfaces. But the one thing that is probably implemented only in our repository is the check that every ELF symbol required from a shared library is actually provided by that shared library. This is called set versions, but other implementations could be imagined. So the first naive approach would be just to put all these undefined symbols into requires of packages and put all symbols that could be used for resolving this into provides. This is more or less similar to behavior of dynamic linker. Why I say more or less? Because it's really impossible to implement dynamic linker in a dependency solver, because it's like really complex, and any attempt will be a simplification, but it's more or less like how it works. But the size of this provides and requires will be prohibitively long, prohibitively big, and resolving all this stuff will be like too slow to be acceptable. So a slightly different approach would be to associate these symbols with libraries. It's also a naive approach because symbol names could be a bit really long. For example, in languages like C++ and other languages that use namespaces and so on, symbol names could be as big as you could imagine and even longer. So while it's somewhat faster than the first approach, because all these names are associated with some libraries, yet they're still too big because of this unlimited length of symbol names, and resolving therefore is quite slow, too slow to be acceptable. So the next step would be to use some probabilistic approach. That is to put not the whole symbol names, which are too long, but just a hash values, and choose hash values of these symbols, and choose the function the way that would produce acceptable false positive rate. What is a false positive rate? When you hash strings into values, there is a chance that different strings will be hashed into the same value. So when you are checking whether this particular string is present in the set of hashed values, there is a chance that a different string hashed to the same value will be found, and this will be false positive. So it's not that risky, because you can actually control this false positive rate by choosing the proper hash function. This way you can reduce the size of provides and requires to the level that can be actually worked with. But besides false positives, you're losing the actual symbol names. So when you can't find, when the solver doesn't find or at least when it detects the situation when requires are not met with provides, there is no information about actual symbol names. It just says that they are not met. What can you achieve in theory if you're using probabilistic approach. Yeah, so if you choosing some false positive rate, you can work with. There is a information theory minimum that is binary logarithm of this rate, which is for 2 in minus 10th is exactly 10 bits. It's a theoretical minimum, but well, if you use something that is popular like Bloom filter, you'll get an additional multiplier by it's about 1.44, which is 1.5 more or less bits per string. If you so yeah, for probability we use is 2 in minus 10th. It's about 14.5 bits per string, and for set versions it's much better. I mean, it's not the multiplier. The theoretical minimum is addition of 1.5, which is like 3 bits better per string than classic Bloom filter. And yeah, the complexity of this is very good. It's big O of the size of requires and provides, and because this requires and provides don't depend on the length of symbol names, it's really good. So how this set versions is implemented? It's a combination of a hash function, which is chosen on the size of the number of strings. What strings? It's functions and variable names. So it's a downgraded Jenkins once at a time 32-bit hash, downgraded to the size that is enough to guarantee us false positive rate we want. For the case of 2 in minus 10, it's just a 10 plus a binary logarithm of the size of the set. So then this set of hashes is sorted, delta encoded, and then compressed using Golomb-Rice encoding, which is natural for this kind of thing. And then it's like converted into a alphanumeric representation used base 64. Base 64 is just 26 multiplied by 2 plus 10. That's why. This way, these sets are human readable. And for decompression, you do essentially the same, but in the reverse order. You decode these base 64 strings and then decompress them using Golomb-Rice coding. Yeah, this is how they look in our system in practice. I've just taken an arbitrary package. It's libdwarf from elfutils. It depends on 3 libraries, and this set version dependencies look this way. Compared to those you're probably familiar with, you can see not just a name, but also a set, and after the colon you see this set version encoded and in base 64 human readable form. And Untitled provides, as you can see, they are much longer than requires. It's often the case when clients use only a subset of this function of the interface provided by libraries. So how good is this compression rate? You remember, it's the theoretical minimum is 10. The theoretical minimum for subversions that could be implemented is 11.5. And you can see in this red line, so that about half, yeah, about half of these libraries, they have bits per symbol ratio 12, and almost all of these have bit per symbol ratio lower than 12.6. So it's more than theoretical minimum, but yet it's much less than you can get using Bloom filters. Also, on this picture you can see that most of libraries are actually not very big. Like half of these libraries have less than 130 provided functions and variables. Okay, so what are the pros and cons of this approach? I'm summarizing. Yeah, you get the guarantee that every else symbol required from a shared library is provided, and the check is performed not at runtime but during package resolving time, so in the beginning of transaction, and performance is quite good. But at the same time, like, the check is still probabilistic, but you can control this. You can choose the rate that is acceptable for you. Anyway, it takes time, so it will, no matter how fast it will be longer than no check at all, but probably not unavoidable. These provides, they are still quite big for big libraries, and even for not very big libraries, they still look like bulky. And the most important, that there is no error diagnostic that would contain symbol names, because all symbol names are lost. We are operating with hashes. Yeah, and base64 is a funny thing. It produces nice, compact ASCII representation, but not as compact as we would like. So, like, base85 would save about 8% of the final size. If you are thinking about implementing all this stuff, you should be aware about obstacles, which are code complexity and integration complexity. Yeah, we use math. I mean, we use some not very common algorithms, and the implementation is heavily optimized for performance. So it would take quite a lot of efforts and time to understand. And some people are really not ready to invest their time into complex things. For example, the main RPM org guy once admitted that this implementation is too clever for his taste and just refused even to discuss this. And with regards to integration, the problem is various projects, they tend to implement comparisons of package versions and releases themselves, and they are not aware about this, and either you would have to teach them to use the algorithms provided by operating system, or make them use this complex code themselves. So it's not that easy. Yeah, this is more or less what we have since 2010. It's quite stable, but we have some ideas for the future. It's really like think in progress. Now, replacing base64 with something more compact is quite easy. There are some results with further optimizing the selection of a Golomb-Rice parameter, if you know what it means. It's traditionally called mbig. It decides what part of how to tune. It's actually tuning of Golomb-Rice coding. It would be backwards compatible. We also have ideas how to check to detect ELF symbol names, ELF symbol version changes. but it's quite complicated because of this resolution process, because well, non-version symbols, they could be resolved either to a non-version symbol, but also to a symbol with any version, and from another side, a version symbols could be resolved also into unresolved unversion symbols. So it's not that easy. Also, we have some ideas about detecting dual level incompatibilities. So like using signatures instead of function names, but not just signatures, but somewhat reduced signatures to ignore insignificant differences. But it's like, I think we're still thinking about, because what is insignificant, like signed versus unsigned, it's mostly insignificant change in practice when you're talking about ABI. On some architectures, long and long are insignificant because they don't differ. They are exactly the same, but the compiler can detect the difference. So yeah, these are just ideas. I have some links at the end of these slides. These slides are uploaded, so you can have a look at these papers and have a look at the code sometime later, probably not now. That's more or less all I would like to tell about this. So if you have some questions, please.
Okay, may I ask? I might not catch that, but basically, what is the core bottleneck? Why you are trying to compress that data? Why you don't use the complete symbols? It will solve a lot of problems. Is the server bottleneck or network connection bottleneck that index would be too large?
Yes, index will be too large, and the check will be too slow because it depends on the size of the whole thing. So comparing hashes is much faster than comparing arbitrary strings.
You know,
indexes will be too large.
My approach would be to build the hashes from the index. So basically, I would completely mitigate this problem, because then I can compare hashes when I calculated them from the index, and it's only just the job of the database manager, and then I have only just problem of the index size, I think. That's at least my opinion.
Yeah, the practice shows that when you are trying to pack all these function names into indexes, they are growing too large, like really too large. And this is 2010 project, so it was even more important like 8 years ago. Yeah. You can try to do this at home. To put all names into your indexes and try to live with it. But
we are maintaining open with WRT different fork, basically our own fork, and we are doing something like this, but we are doing it on the level where we basically are forcing the versions. And we are specifying the build versions of that package where we force specific version, because we have consistent repository. That's the OpenWRT thing. But I know that we have the database that is just simple files with versions, symbols dumped out, and it's not that big. It's around, if I remember it correctly, 4 megabytes or something like that. Yes, maybe in 2010 it was big, but now...
So how many libraries do you have?
Of course, if you are working on big systems,
so
I'm talking about OpenWRT.
In our repository, there are more than 6,000 libraries.
Maybe then bigger project.
Okay, just probably one question, and we're almost out of time. Oh.
We're actually out of time.
Okay, thank you for coming.